everyone, my name is Nur Harisha Aldina binti Muhammad Jari. My matric number is 224508. So today my friends and I, Nur Shahira, Siti Halimatun and Siti Nur Hamiza, will be explaining about the proof that the metric space L squared rho is complete, where L squared is the space of square summable sequences and rho xy equals to summation of k equals 1 to infinity xk minus yk squared to the power of 1/2. So for the introduction, I will explain 3 important things before we go into the actual proof. What is a metric space, what is the space of L squared, and what it means for a space to be complete. So the first one, a metric space is simply a set where we can measure distances between elements using a special function called a metric. This metric must follow 4 rules. The first one is distance is always non-negative. The second one is the distance is 0 if the two elements are the same. The third one, it must be symmetric, meaning the distance from A to B is the same as B to A, and it must satisfy the triangle inequality. So next, the space we are working with is called L squared. This is the set of all infinite sequences of real number like 1, 1/2, 1/3, but not just any sequence. It has to satisfy this rule, which is when you square each term and add them all up, the total must be finite. Then we define the distance on the metric rho in this space. The equation is P xy equals to open bracket summation from k equals to 1 to infinity xk minus yk squared close bracket power 1/2. Finally, we talk about completeness. A space is called complete if every Cauchy sequence has a limit that also stays inside the space. This is important because it tells us that space is stable. If you are working with sequences that are getting closer and closer, their limit won't suddenly escape the space.
Hello everyone, my name is Shahira binti Abdurrahman. So today, our group will produce a short video that clearly and rigorously explain the proof that the metric space is complete, where L to the power of 2 is the space of square summable sequence and rho xy is equal to infinite summation from k equals to 1 to infinity xk minus yk to the power of 2 to the power of 1/2. So let's start with step 1, which is we must prove existence of the limit. So first, we let x to the power of n from n equals to 1 to infinity be an arbitrary Cauchy sequence in L to the power of 2. This means each x to the power of n is an element of L to the power of 2. So x to the power of n is equal to x1 to the power of n, x2 to the power of n, x3 to the power of n, and so on. By the definition of a Cauchy sequence, for every epsilon greater than 0, there exists an n element of natural number, such that for all nm is greater than n, where rho x to the power of n, x to the power of m is less than epsilon. So we substitute the definition of metric rho with summation, infinite summation from k equals to 1 to infinity, modulus xk to the power of n minus xk to the power of m square to the power of 1/2 is less than epsilon. Now we square both sides and we get infinite summation k equals to 1 to infinity modulus xk to the power of n minus xk to the power of m square is less than epsilon square. Now, we consider any fixed component j and is element of natural number. For the sum above, we can isolate the j term, and modulus xj to the power of n minus xj to the power of m square is less than and equal infinite summation k equals to 1 to infinity modulus sk to the power of n minus sk to the power of m square and less than epsilon to the power of 2. So we're taking the square root of both sides, modulus, and we get xj to the power of n minus xj to the power of m is less than epsilon for all nm greater than n. This inequality shows that for each fixed j, the sequence of scalars xj to the power of n, where n equals to 1 to infinity, is a Cauchy sequence in real number or complex number, depending on the field. So since real number and complex number are complete metric spaces, so every Cauchy sequence in real number or Cauchy complex number converges to a limit in R or C. Therefore, for each j is element of n, there exists a number xj is element of R, real number or complex number, such that lim n to the approaches to infinity, xj to the power of n is equal to xj. So we define the candidate limit sequence x equal to x1, x2, x3, and so on. So at this point, we have shown that limit sequence x exists components wise. However, we have not yet shown that this sequence x belongs to L to the power of 2. So I will pass to the member that do the step 2.
Hello everyone, my name is Siti Halimatun binti Abdullah and my metric number is 224792. Alright, thank you Shahira for your detailed explanation in step 1. We have successfully shown that every Cauchy sequence in L squared will converge component-wise to a limit sequence which we denote as x equals to x1, x2, x3, and so on. However, this alone is not enough to declare L squared as complete. Remember the definition of a complete space, where a Cauchy sequence must converge to a point within that space itself. So, our big question now is this limit sequence x truly an element of the L squared space? Or in the other words, is the sum of the squares of its components finite? Alright, so we have a Cauchy sequence x power n in L squared. It converges component-wise to x equals to x1, x2, and so on. And the goal for our step 2 is actually to prove that the summation from k equals to 1 to infinity xk squared is less than infinity. Alright, so we will once again utilize the definition of a Cauchy sequence that we already used in step 1. Recall, because x power n is a Cauchy sequence, we know that for every positive epsilon, no matter how small that epsilon is, there exists an index n such that if we pick up any two terms of the sequence, for example x power n and x power m, after that index n, the distance between them will be less than epsilon. So mathematically, this means that rho x power n x power m is less than epsilon. Or we can write it out as summation from k equals to 1 to infinity xk power n minus xk power m squared to the power of 1 over 2 is less than epsilon. And after we square both sides, we're going to get summation from k equals to 1 to infinity xk power n minus xk power m squared less than epsilon squared. Now we observe this. If the infinite sum of the square of the differences is less than epsilon squared, then of course, any finite partial sum, meaning the sum up to m terms, must also be less than epsilon squared. So, for any finite m, we can write it down as summation from k equals to 1 to m xk power n minus xk power m squared less than epsilon squared. Now, let's use the fact we obtained from step 1, that each component xk power m converges to xk as m approaches infinity. So, we have the inequality from previous slide, which is summation from k equals to 1 to m xk power n minus xk power m squared less than epsilon squared. Notice that this is a finite sum up to m terms. Because the sum is finite, we can interchange the limit operation with the summation operation. So, we will freeze n and m, and then let m approach infinity. So, we have limit m approaches infinity, summation from k equals to 1 to m xk power n minus xk power m squared. And then we take out summation from k equals to 1 to m, limit m approaches infinity as k power n minus xk power m squared. And then after that, we're gonna freeze n because sk power n does not depend on m, and the last answer will be summation from k equals to 1 to m xk power n minus sk to squared. So, since summation from k equals to 1 to m sk power n minus sk power m squared less than epsilon squared for m greater than n, then after taking the limit as m approaches to infinity, this inequality still holds or become less than or equal to. Thus, we obtain summation from k equals to 1 to m xk power n minus sk squared less than equals to epsilon squared. So, it is important to note that this inequality holds for any fixed n greater than n that we choose and for any finite m. This means that the difference between our Cauchy sequence term, which is x power n, and the expected limit x when calculated as the sum of squares up to m terms will always be small. Now, how can we use this to show that summation from k equals to 1 to infinity xk squared is finite? So, we will employ a very powerful mathematical tool, which is the Minkowski inequality. The Minkowski inequality is essentially a generalization of the familiar triangle inequality, but for more complex spaces like L squared. So it states that the length or norm of the sum of two vectors will never be greater than the sum of the length of the individual vectors. So the formula looks like this, which is summation from k equals to 1 to m ak plus bk squared to the power of 1 over 2 is less than equal to summation from k equals to 1 to m ak squared to the power of 1 over 2 plus summation from k equals to 1 to m bk squared to the power of 1 over 2. So now, let's apply this to our situation. We want to know about xk, right? So we can write xk as the sum of two parts, which is xk equals to xk minus xk power n plus xk power n. So, let's say ak equals to xk minus xk power n and bk xk equals to xk power n. So, according to the Minkowski inequality, we have summation from k equals to 1 to m xk squared to the power of 1 over 2 is less than summation from k equals to 1 to m xk minus xk power n squared to the power of 1 over 2 plus summation from k equals to 1 to m xk power n squared to the power of 1 over 2. Right, we have come to the end of step 2. Here's the most exciting part, which is let's choose a specific n that is greater than the n we obtained from the Cauchy definition. For example, let's say we pick n equals to n plus 1. We know from the previous step that for n equals to n plus 1, we have summation from k equals to 1 to m x k power n plus 1 minus xk squared to the power of 1 over 2 is less than equals to epsilon. And we also know that x power n plus 1 is an element of L squared. So what does this mean? It means it's known, which is summation from k equals to 1 to infinity as k power n plus 1 squared to the power of 1 over 2 is a finite value. So we can just call this value as c, for example. And of course, summation from k equals to 1 to infinity as k power n plus 1 squared to the power of 1 over 2 will always be less than or equal to the full norm of c. So we get summation from k equals to 1 to m xk squared to the power of 1 over 2 is less than equals to epsilon plus c. So look closely at this final inequality. We look at the right hand side, which is epsilon plus c. It's a finite constant, so it's a fixed number no matter how large m we choose. Alright, so I will give you like a numerical example. Okay, imagine you have an epsilon which is equals to 0.01 and you know the sequence x to the power of n plus 1 is an element of L squared. So its norm or its length is a fixed number. Let's say the norm of x power n plus 1 is equals to 5. And then we find that the summation from k equals to 1 to m xk squared to the power of 1 over 2 is less than equals to epsilon plus c, right? So 0.01 plus 5 will equals to 5.01. So this shows that the sum of the squares of x component cannot exceed this bound. So no matter how large m we choose. Since the partial sum, which is summation from k equals to 1 to m as k squared to the power of 1 over 2 is always bounded by this finite constant, then we let m approach infinity. The infinite sum must also be finite. Okay, so we're gonna have summation from k equals to 1 to infinity xk squared to the power of 1 over 2 is less than equals to epsilon plus c, which is less than infinity. So we have successfully shown that summation from k equals to 1 to infinity xk squared is finite. So according to the definition of the L squared space, this means that our limit sequence x is an element of the L squared space.
Okay, thank you. So my name is Siti Mohammed Rasman. My matrix number is 225131. So I will explain for step 3, which is to conclude that space is complete. So by showing that Cauchy sequence converge to x in L2 from our original Cauchy sequence x power of n and limit x approaches 0 as n goes to infinity, we need to show that limit n goes to infinity rho x power of n x equals to 0. So from our discussion before in step 1, for any epsilon more than 0, there exists n1 element of integers such that the L2 norm by definition of x superscript n minus x superscript m to power of 2 less than epsilon power of 2 for all n and m more than or equal to n1. So we get the sum k equals to 1 to infinity of epsilon value xk power of n minus xk power of m square less than epsilon square. Next, consider any finite partial sum for m element of natural number. So we get the sum k equals to 1 to m xk power of n minus xk power of m square less than epsilon square. So for a fixed value of n more than or equal to n1, take limit as m goes to infinity. So we get the sum k equals to 1 to infinity, limit m approach to infinity, xk power of n minus xk power of m square less than or equal to epsilon square. So since we know that xk power of m goes to xk for each component k from step 2, so we get the sum k equals to 1 to m xk n power of n minus xk square less than or equal to epsilon square. So take limit as m approach to infinity. We get the sum k equals to 1 to infinity xk power of n minus xk square less than or equal to epsilon square. So by taking the square root both sides, so we get the sum k equals to 1 to infinity xk power of n minus xk square power of 1 over 2. So it less than or equal to epsilon. So this satisfies the definition of rho x and x. So for every epsilon more than 0, there exists n1 element of integers such that rho x power of n x less than epsilon. So for all value n more than or equal to n1. Since every Cauchy sequence in L2 converges to a point that is also in L2, by definition, the matrix space L2 row is complete. So I will pass to the next person. So let's quickly recap the main ideas. The first one is Cauchy sequence. Cauchy sequence is a sequence where the terms are getting closer and closer to each other. They want to converge. Second one is convergence. Convergence is a sequence that actually reaches a specific point, getting infinitely close to it. The last one is completeness. The special property of a space where every sequence that wants to converge is Cauchy actually does converge to a point inside that very same space. Next, I will talk about the significance of completeness. Why is this idea of completeness so important in maths? So the first one is guaranteed existence of limits. Completeness is like a promise. If you have a sequence that clearly trying to reach a point, completeness guarantees that this point actually exists within the space you're working in. This is super important when we are trying to prove that solutions to equation exist, or that a process will eventually settle on a specific outcome. So the next one is a foundation for deeper maths. Many powerful maths tools, especially in areas like calculus and advanced analysis, rely on spaces being complete. For example, the Weierstrass M test uses completeness to show when a series of functions behave nicely and comes together. The next one is the contraction mapping principle. It is used all the time to prove that equation like those describing how things change over time or how heat spreads have unique solution, and for this theorem to work, the space must be complete. So that's all from us. Thank you.